everyone, welcome back. In this video, we will continue with our discussions on qualitative analysis of acidity. We've already looked at two factors that affect the relative acidity of organic acids. We've talked about element or atom effects, looked at resonance, and in this particular video, we're going to talk about a third factor that would affect the stability of a conjugate base, or that would determine the stability of a conjugate base. And this is induction. Okay, induction. And again, this is something that determines the stability of a conjugate base. That is what we use these factors for, whether it's atom or element effects or resonance or induction. We're going to use these for determining the stability of the conjugate base. Now, let's look at some examples here to basically understand what does induction mean, okay? Or not induction, actually, inductive effects, okay? Inductive effects. That is what we're talking about here. It is sort of an effect. And now this effect here, inductive effect, this operates through bonds, okay? It operates through bonds, and this is something that's going to basically weaken with distance, okay? It weakens with distance. We'll look at a specific example to basically talk about whatever we're saying here, okay? So let's compare two molecules here, maybe O minus. Actually, we'll compare a few molecules. So let's say we have that, O minus, and O minus. And I'm going to add one chlorine here. And for this molecule, and we'll add a fluorine over here, okay? These are examples of conjugate bases. So first, let's try to understand what an inductive effect is, okay? And then based on that, we'll try to understand the stability of conjugate bases later. So if you think about the first conjugate base here, we have an oxygen which has a negative charge on it. Now, oxygen is an electronegative element, so that means it should be pretty good at stabilizing that negative charge or holding on to the electrons. When we go to the second species here, the second conjugate base, notice how the carbon chain length is the same, okay? But in this chain, on the second carbon, there is a chlorine attached to that second carbon. So we have a similar situation to the first one, where the oxygen has a negative charge, okay? Oxygen is an electronegative element, pretty good at stabilizing that negative charge. Now, additionally, we have chlorine in the chain, okay? And at the second carbon in this particular case, and I've basically sort of made them similar. So a chlorine here. Now, chlorine, as we know, is also an electronegative element, okay? It would withdraw electron density. So since the chlorine is connected to carbon 2 here, okay, chlorine is going to withdraw electron density from this bond, or this bond is going to be polarized a little bit. So the chlorine is going to have a del negative charge, and this carbon should have a partial positive charge. And that's because the electron density here is pulled towards the chlorine atom, okay? Now that would make this carbon partial positive. Let me draw a big partial positive here. So now this carbon, in turn, is going to pull electron density from this other bond it has, okay, to the other carbon. And so we'll have electron density coming here. So that means this carbon, if it has like a big partial positive, this carbon 1 is going to have a smaller partial positive because electron density is being pulled towards that chlorine atom. Now, remember that the oxygen here is also electronegative, so it would also pull electron density, but we're sort of treating this oxygen as a constant feature between these structures. So that is why we are not talking about the oxygen. But if you're thinking that, oh, the oxygen is electronegative, it should also be pulling electron density towards itself. Yes, that is happening in all of these structures, true. We are looking at something that's additional to that, okay? So that's why we are sort of not considering the oxygen right now. So the electron density gets pulled, and so there will be some electron density pulled from that bond also. So what you can notice is through this electron density, or because this electron density is pulled along the bonds, the negative charge on this oxygen would get slightly diminished because there is an electronegative element somewhere in that molecule. Okay, so the negative charge would get diminished. But like I said, or we'll come to this later actually. So this negative charge would get diminished. That means this oxygen, okay, or yeah, this O minus is more stable than 1. Okay, this is 2. And we'll say that this oxygen, the negative charge, is a little bit more stabilized than the negative charge in 1 because there is no other element that is pulling electron density. When we go to the third structure, we have a very similar structure here, oxygen with negative charge, okay? And we have a fluorine attached to it, and the fluorine is actually pulling away electron density along the bonds again. But if we compare it to the second structure, fluorine here is more electronegative than chlorine. Okay, that means it's going to pull the electron density better. And what that means is this negative charge on that oxygen would get stabilized. This would be the most stabilized, okay, of these three. And so that would be the most stable now conjugate base. So this is the inductive effect that we talk about, and it operates through bonds and it weakens with distance. Okay, what do I mean by that? So let's say if I compare the second structure here to another structure where we have O minus and the chlorine is connected to carbon number 1 instead. So instead of being connected to carbon number 2, it is connected to carbon number 1. In this particular case, the chlorine is pulling electron density towards itself. And as you can notice, the chlorine is closer to this oxygen. There are only 2 bonds between the chlorine and the oxygen. There's 1 bond here, there's 1 bond here. Whereas in the top structure, there were 1, 2, 3 bonds between the chlorine and the oxygen. So in this particular case, the chlorine would be, this negative charge would be better stabilized than 2 as well. Now, I will not be able to compare this structure to that structure qualitatively because fluorine is more electronegative than chlorine, but fluorine is attached to a different carbon. It is farther away. Chlorine is less electronegative, but it is closer to that oxygen. How does that play into stabilizing everything? I do not know. In fact, I do not expect you to know, okay? But when everything is sort of proportional or similar structure, then we would be able to say. So for example, if we had a structure where the O minus was here and the fluorine was over there, okay, if the fluorine was there, then definitely this structure, I can say, is the most stable among all of these, okay? Or it is definitely more stable than this one, for sure, because now the structure is the same. The fluorine is equidistant from the oxygen compared to the chlorine, and so this would be more stable than this. And this would be more stable than that also, okay? And this is more stable than chlorine. This would be the least stable because there are no inductive effects here. Okay, so let's look at some specific examples to see how the inductive effects play out, or how they basically pan out. Let's look at some numbers and then talk about what sort of effects we get from these inductive effects. So we're going to look at a couple of acids here. So we have acetic acid. Again, we're using acetic acid as one of our base molecules. And we know, let's finish drawing all the structures maybe. We have one chlorine, two chlorines, and we have a structure with three chlorines. pKa values for these acids, as we know, this is around 4.7 approximately. And then we have 2.87, 1.25, and 0.50, okay, or 0.70 approximately in that neighborhood. So it's 0.70. These are numbers from the textbook. But if you look at these pKa values, what you can see is that this acid with three chlorines attached to that is the strongest acid based on the pKa values. And we should be able to explain this based on the conjugate base, because when we draw the conjugate base for each one of these, we've got the acetate, we get the chloroacetate, we get the dichloro, and we have a trichloroacetate. So there are three chlorines, so we call that a trichloro. And now, as you can notice, so these are all the conjugate bases. So in the conjugate base of the strongest acid, there are three chlorines at this position. They are all pulling electron density to some extent, and that gets pulled from that oxygen atom. Okay, now there is also resonance possible here, but resonance is a common feature to all three of them. So resonance does not explain the difference in acidity here. Okay, so resonance is common to all three of them, but there is a difference in the extent or the amount of induction that is possible here. So inductive effects are definitely stronger for that last set. And there is no inductive effect here, and we see a difference because of that. Now, in some sense, notice that adding those three chlorines to that molecule, the pKa drops from like around drops by about 4 pKa units, okay? That is a difference about 10 to the power 4 Ka values, or it is like 10 to the power 4 times stronger. That is what we're saying here, okay? So the difference is about 4 pKa units. But for some of the other effects that we've seen, so for example, resonance, if you go back to that video and compare the pKa values, what you would notice is the pKa drops by about 10 units actually, because there is resonance possible. Or when we go to the element effects, you could notice that in going from a carbon to a nitrogen, the pKa drops by about 14, 15 units, okay? So that means those are much stronger effects in stabilizing the conjugate base, okay? So the pKa, the difference in the Ka values, however much that they change for a given effect, they give you some sense for how strong that effect is. So that is something that you would want to keep in mind. Basically notice these numbers so that you're able to do the qualitative analysis effectively. Okay, so that is inductive effects applied to acid strength, how inductive effect can be used to determine or explain the stability of a conjugate base. Bye. Thank you.